There are a couple of limit theorems that we need to know. The first theorem is quite important, and we talked about this theorem before. So the limit of f of x at x approaches to a equals to L if and only if the left and the right have to be the same limit, has to be the same L. I want to introduce to you an example, a function. You know this function is the absolute values function. So we want to show that the limit of the absolute values function of x as x approaches to 0 is going to be 0. So hopefully you remember the graph. The graph of the absolute values function looks like this. So as you can see, left and right, we have the same number, right? But let's just show it. So this is how we define the absolute values function. So absolute values of x equals to x for x greater than 0. Then we have the limit of the function as x approaches to 0 from the right is going to be the limit x approaches 0 from the right of x. So it's 0. Now, for the negative number, so for x less than 0, we have absolute values of x is going to be negative x. Okay, so when you take the limit of the absolute values function as x approaches 0 from the left, it's going to be negative x, and you use that direct substitution, we ended up with 0. So as you can see, we have 0 and 0. Therefore, the limit by theorem 1, the limit at x approaches 0 of the absolute values of x is going to be 0. Okay. All right. The next two theorems are quite important as well. 2 is straightforward. So is so f of x less than or equal to g of x, where x is near a. I'm sorry. When x is near a, then the limit of f and g as x approaches to a is going to be limit x approaches to a f of x less than or equal to the limit of g of x. Anyway, I want to talk about the squeeze theorem. So the squeeze theorem, pretty much you want to squeeze a function g of x in between f of x and h of x. Then the limit of that function, the limit of g of x is going to be the same as the limit of f of x and the limit of h of x, since those two are exactly the same. So this is really, it's a really nice function, and you can see based on the figure, you see, so the g function right here, squeezed in the middle, and then you see the limit of h is right here. The limit of f is right here as x approaches a. And then because g is right in the middle, so we have the same limit. All right, let's take a look at an example. So we want to show that the limit of x squared times sine of 1 over x as x approaches 0 is going to be 0. By the way, you do not want to use multiplication limit for this one, okay? Because we don't have the limit for We don't have the limit for sine of 1 over x as x approaches to 0. So we don't have that limit. So do not use the law. Do not use the limit law for this. Anyway, so we want to squeeze something in between. So we need to find a function we need a function f smaller than g of x, which is this function. And we want a function h larger than g of x. Okay, so we can squeeze g right in the middle. Okay, so to do this, we know that the sine function is bounded between -1 and 1. So we can write -1 sine 1 over x. So the sine function is bounded by -1 and 1. Okay, now I'm going to multiply by a positive number. We know that x squared is always positive for all x. So I'm going to multiply x squared by all of these functions. Okay, because x squared is always positive, so when I multiply, I wouldn't change anything. So we know that it's okay for us to multiply. Now, we also know that the limit x squared as x approaches 0 is going to be 0. And we know the limit of -x squared as x approaches 0 is still 0. Okay, so you can see that I'm going to rewrite. So we have -x squared less than or equal to x squared times sine of 1 over x. And then we have x squared here. So the limit of this one, the limit equal to 0, the limit equal to 0. Therefore, by squeeze theorem, the limit of this one has to be 0.